Up to now, all of the math that we've been doing in pure data has used math objects. When you do math in PD, it can be quite cumbersome to connect multiple objects together to execute a single equation. You'll have to worry about bang order. You'll have to use a trigger in some cases to make sure that variables are loaded into the cold inlet before the hot inlet is banged. And so we'll go over in this movie the expression object, which allows you to type out mathematical equations on single lines and more efficiently run them, especially when you have equations that have different orders of operation. So here we have the basic Pythagorean theorem, which is a squared plus b squared equals c squared. So I've got my a squared here, which is message box 4, an int going into pow2, and this is how you use exponents in PD. Use pow and then the exponent that you're going to use, so 2 since we're squaring. 3 squared, I would add them together. I use a trigger to make sure that the 3 squared is banged first, and then 4 squared. Get the result, and then to find out what c squared is, I've got to take the square root of that. And so when we bang this, we get the answer that a squared plus b squared is 25, and the square root of that is 5. Now this is all fine and dandy. It's a very simple equation that involves different objects for math, but what we're going to do is we're going to type out the same object using the expression object. So now we'll unlock the patcher, copy the top part, because we're still going to trigger the bangs in the right order. But now what we'll do is we'll create an expression object. So place the object expr, then space. And now when you're typing out an expression, this is going to be very similar to how you're going to write math expressions in C or in other languages that are not data flow languages. So since we want a squared plus b squared equals c squared, or we got to get the square root of c squared, what we're going to type is $f1, and so this is going to stand for our first variable. The F stands for float. The $ tells PD that it's a variable. So you'll see in a minute this will create an inlet. Okay, and then around that, pow parentheses, comma 2. Okay, so this part of the expression is equal to the 4 going into the pow2 at the top. Okay, and then so the b squared part would be, again, I start with what the b would be, was f2, and then I work around it. Pow parentheses, then comma 2. Okay, so right now this is just a squared, that's f1 squared, plus b squared. Then what we have to do is get the square root of the result. So what we're going to do here is we're going to surround the entire equation with parentheses, and then go back and type sqrt. So since you're working with the expression object, you'll really have to be careful about order of operations. If you don't remember, that's please excuse my dear Aunt Sally, or parentheses, exponents, multiplication, division, addition, and subtraction. So here we're working from the inside, and then we're working to the outside, the square root. So the pow f1, 2, that's this part here, the 4 in pow2. The pow f2 and 2 is the 3 in pow2 up here. And then the square root part is the sum of these two. It's right down here. And you'll see there are 2 inlets created. Each one corresponds to the $f1 and $f2 respectively from left to right. So what we'll do is we'll connect the 3 to the cold inlet, and then like other objects, the leftmost inlet is not only an inlet to take in data, but also it fires the equation. So we still have to bang this equation. All right, and then we need a number atom for the result. All right, and then lock the patcher, and there you go. There's the answer. So you can see that in one object we've contained code that we took up with actually just 3 objects from above. The number atoms are there just for debug purposes. We truthfully could get away without it. But you can see that it's much more efficient in terms of space, and we'll also take a look at how you can use lists and the order of numbers in lists to process, or to do math rather, and some really cool conditional logic that can be done with the expression object. Another great feature of the expression object is that you can use one expression object to process multiple equations. Each equation will have its own outlet. So I've got my 4 message and my 3 message, these ints from my previous example. And what I'll do is I'll create 4 separate equations that will use these numbers as input. And these equations will just be to demonstrate multiple equations. Later we'll actually do a meaningful example that will check the distance between objects. So I'll create my expression object, expr, and we place this. Now what I do is after that I'll type f1 plus f2, and this is $, by the way, f1 and f2. I'll just say f1 and f2. Now I'll type semicolon and hit return and type my next equation, $f1 times f2. So that's the first inlet times the second inlet. Remember that the f stands for float in this case. You can actually use I if you're if the numbers coming in are supposed to just be ints, and you can also do symbols. That would be s. So then f1 divided by f2, and we'll do our square root again. Pow parentheses f1 comma 2, so square root of, or I'm sorry, f1 squared plus pow parentheses f2 2. So this is the start of our Pythagorean theorem example that we did earlier. So there are 4 separate equations, so when I click off the box I should get 4 outlets, and I do. So now I've got 2 inlets. Each inlet corresponds to the $f argument. So f2 over here, f1 right here. Tidy this up, and I'll create 4 number boxes, or number atoms rather, and connect them. Oh, and that one I accidentally slid, so that's why it says 1, but no worries. Alright, and lock the patcher and fire the equation. And there are the results. The first equation was f1 plus f2, so 4 plus 3 is 7. The next one was f1 times f2, so 4 times 3 is 12. And then f1 divided by f2, so 4 divided by 3 is 1.33, and actually more. And then 4 squared plus 3 squared is 25. So in the next part of the movie, we'll take a look at how we can use lists with the expression object in order to process math within lists. When you feed a list into the expression object will read the list from left to right according to the variables that you assign in your equation. So for example, if I type expr, and then if I wanted to add all of these numbers in this list together, I would say $f1, that would be the number 3, the first number in the list, plus $f2, the second number, plus $f3. This would also create 3 inlets, but since the numbers are fed in order into expression, I can just use a single list to process the equation, and when I bang the list, I'll get the result of my equation. So all of these numbers added together are 30. And just as we did in the previous example, you can say, okay, well, semicolon, and then do the next line. So what if I wanted to do 3 times 8 plus 19? So that's $f1 plus $f2. And since you want to get that result first, put it in parentheses. Oh, I said times, not plus. So asterisk, then plus 19, which is $f3. Now that's going to create another outlet because that's a second equation. And then when I bang the equation, I should get that result. So 3 times 8 plus 19 is 43. And you can still use the inputs of the expression object. You'll have to remember the order by which the bangs are received into expression. But this is really helpful because you could conceivably get a list of numbers, floats or ints, and you could pack them into a list, and you could more efficiently process them into a single outlet. Or you could even have a list that is affected by other inlets, though the uses would be right now hard to come by or hard to think of. But in the next example, or I should say later, we're going to take a look at distance. Where the expression object really starts to show its true potential is with conditional logic. Up to now, we've used Spigot and Moses, and as well conditional operators to create conditions by which certain things would be true or false, and then results would happen. But you can do this using the expression object rather easily. We'll create an expression object, and you would use the syntax for an if-else, like so. So if, and then start your parentheses and close them. That's just good habit, so that way you're not forgetting to close your parentheses. And then within the parentheses, the argument goes like this. If x, comma, then output y, else output z. And what we're going to do is we're going to fill x, y, and z with equations. So x is the condition to be tested. So let's say with the numbers above, if f1, which is 4, is greater than f2, which is 2, then output, let's say 1. Else output 0. So there we've filled our x, y, and z. Now, these numbers are static. They're not going to change. And we only have 2 inlets because we haven't designated an f3 in any part of the equation. But that's okay. We'll deal with this first. Okay, so if f1 is greater than f2, if 4 is greater than 2, output a 1, else output a 0. Okay, so that was a no-brainer. We could see that's easy. But we can also do this. We could say if f1 is greater than f2, output, instead of a 1, output f3. So if 4 is greater than 2, output 7, or whatever's coming into that number. And actually, here, let's make it interesting. We'll connect a number atom. And we haven't banged it yet, so the number in there is 7. So if 4 is greater than 2, output 7. We could even change f3. Notice how it's not banging the equation because the hot inlet is not being banged. But now it should output, one more thing. We have to connect, we have to bang that in. There we go. And now it's 35. Yeah, so expression isn't going to store the f3. That's an important point. We can change it, but it needs to be all processed at once. So that's an important point. So remembering that we can do multiple expressions, let's disconnect this number atom, connect the 7 back up. We can make equations that are a little more sophisticated, and that essentially would be the equivalent of creating a Spigot or Moses, where under certain conditions the equation would fire and would give you the result, or if not, it would give you a 0. Or in the case of Moses, we can have numbers going out of one inlet or numbers going out of another. Actually, that would be good with 2 equations. So what we can do here is on another line, if, let's back up. If, and then open and close the parentheses so that we know we've got it happening. Let's see, we can say if f1 is greater than f2, and what we do is we'll use double ampersand for and. So and f2 is greater than f3, comma, so this is now, then do what to execute if it's true, output a 1, else output a 0. So what we're saying is if 4 is greater than 2 and 2 is greater than 7, give us a 1, else give us a 0. So obviously we're going to get 0, but it's okay. Remember, since this is the second equation, it's going to come out of the second outlet. Okay, and then fire, and we get the 0. Also, we could say, instead of give us a 0, let's give us f3, and we'll square it. So pow f3 comma 2 and the parentheses. And so if f1 is greater than f2 and f2 is greater than f3, give us a 1. Else, give us the square of f3. So it's a pretty expressive, well, pardon the pun, a pretty powerful object in that you can do lots of different math which would require multiple objects in one line, but you are writing expressions, so you're going to have to be very careful about your order of operations, your use of parentheses to force the order of operations so that your expressions calculate correctly. So in the next example, we're actually going to use this meaningfully. We're going to use it to check the distance between objects in the Reactivision system. And so objects will be in an xy plane, and as we move one, it'll check the distance against another. In this last example, I've set up a patch that uses the 2EO demo files provided by the Reactivision folks in order to get info out of the 2EO client, which we used in an earlier movie, that will track fiducials on a table. And instead of firing up the camera and having fiducials, I just decided to use the 2EO simulator, again available at the Reactivision SourceForge site. So what we're doing is we're looking for the update object message that's coming out. I'm using ZL Slice to take off the session ID. If you want to know more about the ZL objects, just type it in PD and look up the help. They're really good for processing lists. Then I'm routing fiducial 1 and 4 to two sides and unpacking x and y for each of those. So here on the left I have x1 and y1, that's for fiducial 1, and then x2 and y2 for fiducial 4. And as I use the simulator and drag these out, you'll see then that we get results. So the main idea here is that if the two fiducials are closer together, we'll bang note 60, and if they're further apart, we'll bang note 67. And we'll accomplish this by sending a 0 or 1 according to the expression that we define. So what we're going to use is the Euclidean distance formula to find the distance between two objects in xy space, because we could just look at the distance between x's or y's, but that's just going to give us distance one-dimensionally. We want to look at it in 2 dimensions. So I'll start by typing expr, and the formula is x1 minus x2 squared plus y1 minus y2 squared, and then you take the square root of that to get distance. So it's a pretty big equation, but we can handle it. So first thing we need to do is say f1, so that'll be our x1, minus f3, because we're going to pipe the numbers in according to x1, y1, x2, y2. Okay, and we want to square this result, so pow and parentheses 2, so we're squaring that. As well, it would be a really good idea to get the absolute value in case the objects weren't left to right 1 and 4, so we'll type ABS and surround the f1 minus f3. Okay, so that's one aspect. That's the x1 minus x2. Now we want to add that and do the same thing. So y1 is going to be the second inlet minus y2, which is the fourth inlet. This time let's get the absolute value of that, ABS, and I've already typed the parentheses, and then let's square that and go back here, pow, and don't forget after the absolute value part, this is where we're going to square. And then we need to get the square root of the entire equation. So surround the entire equation with parentheses and type SQRT. So there we go. We've got our 4 inlets. All right. And now I'll start piping in numbers. So I'll do it from right to left order. I'm not going to use a trigger here. So I want y1, and then x1, I'm sorry, y2, x2. Now, according to this model, I'm going to fire the equation after x1 has been received. And right now, we just want to see what the result is. So we'll do that. Come over to the simulator. And as we move 1 closer to 4, the number decreases. As we move it away, it increases. And since the equation is fired by the first fiducial, if I move the second, it's not going to fire the equation again. That is a little bit problematic. For the sake of just going over how you would use the distance formula here, we'll leave it as is, as if, fiducial 1 is going to fire the equation. But essentially what you would do is you would connect a bang from the fiducial 4 into fiducial 1's results so that it was firing no matter what. But anyhow. Okay, so what I want to do is create a logical condition. Okay, so I'm going to then take this entire equation, which is giving me a result, and surround it by parentheses. So you see how I'm working from the inside out. And then I'll type if. So now remember, it's if x, then y, else z. So I have the x part. That's the entire equation. So what I'll do is I'll take this entire equation and I'll say is greater than, let's say, 0.5. It's giving me floats. Then output a 1, else output a 0. So if the distance is greater than 0.5, output a 1, which will then bang this here, else output a 0. Okay. Now I'll lock it and move the again. So 0 and then 1 because they're pretty far apart. So now the idea is to pipe these results into our make note. So if the result, if the distance is greater than 5, bang note 67, else bang note 60. Oh, of course, no wonder it's not working. It would help if I connected the outlet of the expression into the select. That would be useful. Okay. So if it's greater than 5, bang 67. If it's less than 0.5. And we're getting a continual bang, so let's save ourselves the headache and type change. We'll disconnect these two. Well, actually, we'll put it between make note and note out. So it'll fire once. Otherwise, it's going to keep banging as it checks the distance. And then put that into make note. Okay, so we just breached it. Now it's greater, and then less. So you can, I think it's really apparent how this can be used expressively, because if you have a whole bunch of objects on the table, just imagine what this would look like if you were using straight up PD math objects instead of the expression object. It would look pretty unwieldy, but this gives you an opportunity to use a single object to process a very complex equation, but also, you remember, you can have multiple equations in the same object and have different outlets for the results.